Okay, welcome PCS members, welcome friends, and welcome our advanced study group participants. Today we have a pleasure of hosting Mr. Lorenzo Celiberti from University of Vienna in Austria. And this seminar is a contribution to the advanced study group with the title Computational Study on Strongly Correlated Low-Dimensional Magnetic Systems, whose convener is Professor Chang Jong Kang from Chungnam National University. And I ask Professor Kang to introduce our speaker.
Thank you, and thanks for coming. Okay, so let me introduce our speaker, Lorenzo Celiberti. She got a bachelor degree in physics in University of Bologna, Italy, and now she is a PhD student in computational material physics in University of Vienna. So we'll talk about the Jahn-Teller polaron in this system. So welcome our speaker.
Thank you very much for the nice introduction, and thank you to the organizer of this seminar and also the Austrian-Korea collaboration that gave me the possibility to be here in Korea and presenting this work to you. Polarons is spin-orbit coupled materials. This is a kind of novel thing since polarons. Now we will see what polarons are and what these materials look like. But these kind of polarons were previously studied only in different classes of materials. And so this is more or less the structure of this talk. I would like to just briefly and roughly introduce some concepts that will help us in understanding this work, and maybe this can be boring for you. I'm sorry for that if it is boring. And I will also introduce some materials, consummated and barium calcium osmate, to show some features of these materials, and then we will focus on the last one, barium sodium osmate, where we will look for polarons. So the first character in this story is spin-orbit coupling. Spin-orbit coupling is known since the early days of quantum mechanics, but like the last century, in the last decades, a lot of new interesting phenomena has been reconstructed to spin-orbit couplings as topological phases, spintronics, astrophysics. And what we will focus today on is especially non-collinear magnetism. Here, I managed the pointer is the one up there. So this is an interaction between the orbital moment L and the spin moment of the electrons that arises within the framework of Dirac equation. So this is a relativistic effect. And what we need to know that in our talk is this interaction has a coupling between lattice and spin degrees of freedom. And in this way, the zeta component of orbital momentum and spin momentum are not a good quantum numbers anymore. And we have to introduce a total angular momentum. What this means is that the orbitals are basically changed by this interaction. So here in the first row, we can see the d orbitals with these shapes. But when we introduce the spin-orbit coupling, they're transformed in these more complex shapes here. This is just example for different cases, depending on the orbital occupations. Another point which is interesting for us about spin-orbit coupling is that this interaction is stronger for heavier atoms. So here you can see maybe these are very little points. These are calculated, whereas the lines on top of the gray region is extrapolated behavior. And so we can see that as we increase atomic number, also the intensity of this interaction is stronger. So this already tells you that to find compounds with strong spin-orbit coupling, we have to look at the lower rows of the periodic table. The second character is electronic correlation in crystals. So just very briefly, but I imagine that all of you knows this. In crystals, we have translational symmetries for a system. So with the block theorem, periodic boundary condition tells us that the spectrum of the electrons has this band structure that we can calculate it with our supercomputers. And also this, just wanted to, from the model Hamiltonian guys, usually represent this with in the block basis with a kinetic term, basically, or this second term, this second form here is in the localized basis where the ij sides are the position of the crystal sides. But just to have this in mind, it's not really important now. We calculate this band structure with density functional theory, which basically tells us the ground state property of the system are encoded in the electron density. And thanks to the constant theory, which tells us that we can basically map our interacting system to a non-interacting one, solving this self-consistent equation for the non-interacting one, and we get also the property of the interacting system. And this is done nowadays like every day, basically, for understanding materials. The problem is how we account for electronic correlation, electron-electron interactions. And the classical way is to use the local density approximation, LDA, which is kind of rough. And in fact, for some materials, it doesn't work. Oh. Okay, now I'm going too fast. Okay. So these materials where the LDA fails are usually materials with strong electron-electron correlation, which can be represented with in a model Hamiltonian by the Hubbard model, which is not solved yet, as far as I know, but many people are working on this. And this is this kind of interaction term is which represent the Coulomb repulsion between electrons on one side, are necessary to describe Mott insulators. These are materials that are predicted to be metals from the standard band theory, but are actually insulators because of this Coulomb on-side repulsion. And where we can find these materials, these are at least the first ones that have been found were transition metal oxides, in particular 3D transition metal oxides. So materials containing first order transition metals. Among them, we have like materials such as nickel oxide, titanium titanate, titanium manganate, and so on. If we look at bevel transition metals, we have these general trends of the electronic correlation on the left, U, represented by the upper parameter U, which is stronger for the first order transition metals and is weaker for as we go down. And this can be understood by looking at the orbitals of the electrons. So if we look at transition, because we have that for 3D electrons, the wave function is much more localized. So the probability that the electrons are close to each other is much higher. So they repel much more. Whereas as we go down, the wave function is more delocalized. So probability that the electrons come close to each other is much smaller. And on the other hand, as we saw at the beginning, spin-orbit coupling increases as we go down to periodic table. So now the question is, can we find materials where both effects are strong? The answer is yes. And these happen especially in some osmium and iridium oxides.
Sorry, can you maybe remind again why you want to find this combination of strong interaction? What was the motivation?
The motivation, I guess, is much related to, it's a theoretical motivation. So what happens when we put this effect? How the physics of our system changes? So and also is like, so apparently now I will come with the next slide to see one material in particular, which was the first one in this in this class of command, which is the strontium iridate, which so this material is an insulator experimentally, but from the band picture, this comes like a metal. So why is it like that? So if you try to add the Abbott correction, you need like an extremely large value, a physical large value of the U to open a gap. So, but this doesn't work. But if we introduce spin-orbit coupling, then you, with a U of 1 electron volt, you open the gap, and you find that you manage to reproduce the physical property of this material. So this also has been called a Mott spin-orbit coupled Mott insulator. This was the first material we found in this class of compounds. And so what we see here.
But I'm sorry to interrupt you. But you mentioned also the Hubbard model, which also opens kind of like a gap, so it becomes an insulator, right? But what you see here is that would happen in these materials language in too large values of the interaction.
Yeah, basically, you would need something, if I remember correctly, a U value to a gap of 12 electron volt, which for these 5D transition metals is very high. Usually the U is 1 electron volt. Like for the 3D transition metal, which are the materials with a larger U, you have something like 6, 7 EB. So this is for 5D, it's really large. Whereas when you add spin-orbit coupling with a U of 1 EB, you manage to open the gap. And you have, because if you look at the orbitals, so you go for the D orbitals, you have the crystal field, so the splitting of EG to G. Then you have the factor splitting of spin-orbit coupling in the pseudo-spin multiplet J3 halves, which is full here, this strontium iridate, and this half field doublet. So as you add the Hubbard interaction on top of this basically splits in the upper and lower Hubbard plane, as is depicted in this picture here. So this is basically how has been explained the electronic structure of this material. And another effect of strong spin-orbit coupling, which is seen in this material, is the appearance of non-collinear magnetism. Non-collinear magnetism means that you have magnetic moments not aligned along the same direction, as you can see here. Where you have so the green arrows at one angle, you have the blue one at a different angle. This is usually not 90 degrees or 180 degrees, as is in normal ferromagnets or antiferromagnets. And especially due to this spin-orbit coupling, this is entangled with lattice degrees of freedom. So you can see here that you have different magnetic configuration depending on the geometrical parameter. So you have this canting angle coming together with a rotation of the iridium-oxygen octahedron, characterized here by the angles theta and alpha. And so here, this was the first example, but in this region of strong interaction, of strong spin-orbit coupling, a strong correlation, many exotic phases can be found. This is just actually this from 2014. I think that now something more can be added to this plot. And so we have very exotic phases as by semi-metal, topological Mott insulators. And here on the top, we have the quadrupolar or multipolar magnets. That is what we are interested in now.
Could you please comment maybe what does axial insulator means in this context?
It's a good question. I don't know the answer. I'm sorry for that. I don't know. I'm like, I studied something within the multipolar magnets, topological phases, something like that. But I can't really explain all this variety of
So I think that as your insulator, you get topological insulator when you use the red and degree freedom, and that's theta term in the S1 function.
Thank you.
But it's in any way a sketch. I mean,
Yeah, it's
not
really, yes, it's just indicative to see like that the interesting phenomena characterized by the cooperation of these two interactions. And so now, among these, maybe we could be more interested in other ones, but I happen to study these multipolar magnets.
Once we interrupt you, can you go 2 slides back, please? That's for me to understand. Yes. So the spin-orbit coupling in this upper example, this Mott SOC insulator, what does it do mainly? Is it reducing the density of states at the Fermi energy? Is that its main thing by removing some of these degeneracies there?
I mean,
and then the interaction
yes.
and then you need less interaction to open the gap.
Yes, basically, yes. As you can see from this splitting you have here, you have just a degeneracy of 2, and then this band is split by the Coulomb interaction.
So I also have a question. So in this case, you consider the spin-orbital coupling first, make this to be a half-field band. Then you apply the upper so that you have the half-field. But in this case, you need to have the spin-orbital coupling stronger than the upper from the beginning of the switch.
You mean like to do the opposite, like
yes, we have the upper interaction stronger, first and then turn it on.
So, as far as I know, this has been done with DFT. So, and then
so it's,
you can, I mean, either you switch on spin-orbit coupling, you can do a calculation, then you can also switch on part correction, but it's not something that you do one on top of the other, like in successive steps. So, basically, you have both. Okay. So, multipolar magnetism. Here, just as now, I imagine all of you knows that, like, usually for magnetic insulators, we study the magnetism with spin Hamiltonians, like the Heisenberg Hamiltonian, which is the most common one, where you have this coupling of the spins as I and J at different sides of the crystal, coupled with this constant J, I, G. But with some spin-orbital couplings, this can be not enough. And we need more complicated terms where we have also higher order products of the spin operators. And this can be represented with tensor Hamiltonians, where you have the multiple operators O. And you can see that this formally, it's very similar to the Albert Hamiltonian, but these operators can give account of much more complicated interactions. And another consequence of this, of the presence of these operators is that you can have the so-called even orders, where you have an ordered phase where you don't have magnetic moments ordered, but another order parameter, which are these multiples operators. An example of this is the barium calcium osmate, which shows a ferro-octupolar order, meaning that you have octuples ordering, so tensor operator of rank 3. And here you can see the interactions constant between these multiple operators calculated within the dynamical mean field theory and Ba2NaOsO6 approximation. And you can see that there is a dominant interaction in this region here, which is the octupole interaction. The second example, which will be the one we will stick all the way along the end, is barium sodium osmate. This is also material featuring strong spin-orbital coupling and strong electronic correlation. Actually, here we have a U which is typically much larger than the usual 5 dB values. So we have about around 3.3 electron volt, 3.5. This also comes from CFPA calculations. And this structure you see here is the double perovskite structure, where you have alternating octahedra, in this case of sodium and osmium. And so this material presents a canted antiferromagnetic ground state, which from model Hamiltonians has been shown to be driven by quadrupolar interactions, so beyond the dipole-dipole interactions. And also NMR measurements shows these complex ground states together with Jahn-Teller distortions. So the octahedra, is a local distortion of the octahedra which shows reduced symmetry. So also my former mentor, Ba2NaOsO6, performed FT calculation on these compounds. In particular, he calculated the total energy as a function of the canting angle of the magnetic moments. So you can see, so these blue balls are the osmium atoms with magnetic moments aligned on the XY plane, and you have you basically vary the angle on the plane, rotating these magnetic moments like this. And what you observe is this curve showing a minimum at around 67 degrees for this canting angle. And this is in agreement with NMR measurements, which gave 66 degrees for the canting angle. With the same kind of calculation of the barium calcium was made, they calculated the multipolar couplings. So where you can see here this strong quadruple interaction, and also you have some small dipole octupole interaction. So this canted phase is driven both from Jahn-Teller distortion and these higher multiple interactions.
So to have some better understanding, just want to ask, so you have both this antiferromagnetic like ordering and also octupolar simultaneous.
Yeah, because what you see here is magnetic dipoles. You don't see octupoles. Or, I mean, the quadruples, you see quadruples from the Jahn-Teller distortions.
Quadruples.
Because they're connected also to the Jahn-Teller distortion.
But how you can probe this hidden orders? Maybe you can comment more on them.
So I remember correctly, I think you can see trace of these hidden orders in the neutron inelastic scattering experiments. But I'm not sure about experimental techniques to say this.
It's easy to use neutrons for this like conventional orderings.
So yeah, I know that it's very difficult to see experimentally these the trace of these hidden orders. That's why they're called also hidden orders. But I don't know the very details of how they do the measurements.
What about Rex?
Rex? Yeah.
Rex or absorption, emissivity.
Yeah, I think you can do. I don't know. Honestly, I don't know about experimental how you can move them. But yeah, probably you can do that. Also, maybe with the rigs, you can do that.
And how we can intersolve this table that you have. These are the table of the interaction,
yes,
of the multiple interaction, and 3 correspond to octupole.
Yes.
So
yeah.
And so how shall I read that there is some interaction of different signs between octupoles?
Yeah, you can. Yeah. So basically.
But there are also quadrupole with 2.
Yeah.
And almost not dipole.
Yeah. Yeah.
I guess the point is it more important that you have on the diagonal for the dipole nothing and instead something on the higher order, or is the off diagonal structure that is important? So you're interested in, you know what I mean?
Yeah, I think it's more like so. It's more important the diagonal, because in that case you see here you clearly see that you have this coupling between quadrupoles.
Mm-hmm.
So this interaction is stronger than others. Yeah. Then you have also cross interactions, but so in this case, yeah, I would say it's your maybe.
So the largest entry is on the diagonal for the quadrupole. That's yes. What you are focusing on now.
Yes.
But this is depend on the interaction. Two electrons is the XY plane in two osmium is located in the XY plane and located in the YZ plane and located in the GX is different, right? This is cubic symmetry and
this is cubic lattice.
Yeah, so this is the result is
nearest neighbors
in the XY plane.
Yes.
YZ and GX is also rotated over the 90 degree or
I mean, like, if so, this if I remember correctly, this has been calculated under the FCC lattice with symmetry. So either you take this plane, or you rotate the system should be invariant, right?
So you're watching the cubic, but the Jahn-Teller case is different. But you're watching the cubic, maybe different. You neglect of the 0, 1, 0, and something, but you consider the other plane, not 0, is maybe 1 plus. So you take over the 1, 0 state, maybe 2 or 1 minus 1 plus is 0, right? If you do,
so in this case, 0 corresponds to the zeta axis.
But the other part is the C is maybe Y and X.
Yeah. Well, we well understand how would the system react if we apply external magnetic fields if we have only conventional magnetic order, this antiferromagnet. Can I find some traces of this hidden order when I apply my field, for example, in some phase transition fields in some phase transition fields?
So
if I try, for example, to polarize my magnetic moments with external fields, we can calculate without this hidden orders, for example, a critical field which correspond to this phase transition. Can I observe some traces of the hidden order in such a quantities?
So, I mean, you should. I think you should measure something related to your other parameters in this case. In this case, would be like, for example, quadruple operators. But so if you measure that, you can see that it's transitional. That, for example, if you can calculate the acceleration function of this quadruple, you can see if you have an ordering. But I don't know how you can measure that. I don't know the answer to this question. Okay. So so we have this multipolar this canted phase driven by multipolar interactions, and
So these calculations are zero temperature calculations or higher temperature?
So this, I guess, are the zero temperature calculations. So yes, we have this canted ordering with multipolar interactions and Jahn-Teller distortions. So this point,
I mentioned why it's not because of the breaking mode. Q1 mode. Q mode is dominant. The Q1. You only Q2, Q3, and trigonal Jahn-Teller. Breaking mode is also important.
Q1
is
So I mean, this is just a sketch to show like what I mean with the Jahn-Teller distortion. So this like reduced symmetry of the octahedra. Q1 mode is actually isotropic expansion or compression of the octahedra. Okay, so it depends on like also the reference structure with respect to your measures. Okay, so if you take 0, so how to say, like with the Q1 mode, you're not lowering the symmetry of the local environment because the octahedron is perfect. Whereas with this other one, you have a lowering of the symmetry, which also splits the level.
The sodium site is really independent. Easy to move.
Yeah.
So that it means the reading mode is somewhat easy.
Yeah, you can have it, but so what is like what we will see like later, like it's more important in our case, more like this tetragonal distortion and orthogonal distortion. But maybe we can discuss this also later, because otherwise I don't know if I managed to explain. So at this point, I guess everyone knows what is the Jahn-Teller theorem. So you have orbital degeneracy, which is unstable with respect to lattice distortions, and therefore you expect that some distortion take place and you reduce the energy of your system. And this is an example of what can happen on the multiple of the level structure of our material. In this case, you have manganese 3+ ion. You have the splitting D2GG of the crystal field, which is further splitted by this tetragonal distortion, which basically means that you, for example, you compress on one axis the octahedron and expand on the plane, or vice versa. And here you have the definition of some modes, so the breathing mode Q1, orthorhombic, tetragonal, and one trigonal mode with respect to the coordinates of the for example, oxygen, osmium. Okay, and I will see. So the splitting you have there, it's because of this kind of distortion here to treat tetragonal, and this is also what we're interested for the polaron. And another question which is interesting is that how this Jahn-Teller distortion interacts with spin-orbit coupling, because as we saw at the beginning, spin-orbit coupling is changing the shape of the orbitals. So it's also changing the charge distribution within the octahedron, and especially in this case, for the Q3 distortion in a D1 Jahn-Teller impurity, these are results of exact diagonalization for an impurity model. These show that spin-orbit coupling quenches the Jahn-Teller distortion. So as you can see in the plot on the left, the red line. Whereas on this plot on the right, you have the Jahn-Teller energy, which is the energy difference between the undistorted configuration and the distorted one. And you see that this energy gain is basically decreased as you go at stronger spin-orbit coupling. So you have a competing interaction between these two. And this will be also interesting for Polaron physics. So these are, let's say, a recap of what you have seen now: strong spin-orbit coupling, strong electronic correlation, Jahn-Teller distortion, and canted magnetism in this barium sodium osmate. Now we're interested in the doping of this material. So what has been done is to change sodium atoms to calcium. This basically introduce electrons in the system, which has been shown to localize around the osmium site, from the calcium to the osmium. There's this charge transfer, and different concentration has been measured. In particular, not any concentration, you don't see any insulator to metal transition. This stays insulating from 0 calcium to full calcium. It's always an insulator. And so the idea here that came was, how is this possible? Usually, for example, something iridate, you dope with electron, you get a metal. And usually this is always what happens. When you dope, it's really likely that at a certain concentration, you have an insulator to metal transition. So the idea here was that the formation of polarons was hindering this transition. Polarons are quasiparticles, which are formed in polarizable materials, where you have a charge carrier, which is basically self-bound. You have a carrier, this displaces the ions, which in turn produce an electric field, and the charge carrier can be trapped in this electric field. And this is basically a consequence of strong electron-phonon interaction. You usually do two kinds of polarons can be distinguished with large and small polarons, depending on the dimension, on how large is the distortion. If you have something larger than one lattice constant, typically you speak about large polaron. If it is smaller, you speak about small polarons. And so this is what we can see, especially from the FT calculation. So on the left, you see you take an undistorted lattice with another electron. This electron will fill the conduction band, and you have a delocalized state. Okay? But what can happen in these materials is that the lattice is distorted, and you get a localized state in the insulating band. Yeah. And you can define a Polaron energy, taking basically the energy difference between these two calculations, which corresponds to the red and blue curve in this case. So now what happens in our material? Our DFT calculation show that the polaronic solution is more stable. And here you can see these blue and red shapes, which is the charge isosurface distribution, which is well localized within one osmium oxygen octahedron. And whereas the white one is the charge density of the other T1 bands of the osmium sides. And we also performed the DMFT calculation here to show the multiplet structure of these sides. And basically you see that at the polaronic side, you have a J effective 2 state, whereas at all other sides, the J effective 3 structure is preserved. So you have a phase where these two different spin-orbital structures coexist together. If you look at the band structure compared to the pristine case, you have on the left the band structure of the material without doping. And you see, so the dashed line is Fermi energy. You see this bunch of bands corresponding to the osmium the electrons, the occupied ones, whereas you have the D unoccupied state above. And when you do the doping, you have the formation of these two states corresponding to the polaron. So calculating the charge density of these two bands gives you the shapes I showed you before. Now, the next step was basically to study the dynamics of this particle, and especially this also came from some observation in nuclear magnetic resonance experiments. So NMR, just a recap, we have sample in a magnet so that the nuclear spins in our material are precessing at the Larmor frequency, and then you perturb with an oscillating field the sample, and if you perturb at the Larmor frequency, the system of spins absorb energy from the circuit, and you observe a signal on your circuit. So what has been done is this saturation recovery measurements, where basically first apply a pulse, the spin are flipped on the plane, then they start to dephase, so you don't see anything. After a delay time tau, you apply another pulse, so that the spins change directions on the plane, and then after another time tau, they are again on phase, and you observe this signal here. And the amplitude of this signal is directly is proportional to the magnetization along the z-axis of the sample. And now measuring, the point is that when you have this, when you flip the spins due to the perturbation, due to the interaction with the lattice, this tends to go back to the equilibrium value on the z-axis. The time that it takes to go back is called the spin relaxation time T1. And to measure this, usually one reproduces these measurements at different times tau, unit times tau. And the most simple case, you have this kind of relation, and you can fit to your experimental data and extract T1. At the microscopic level, what you have is, for example, your nucleus is spin 1/2. You have a splitting due to the Zeeman field or the static field. And you basically have transition between these two levels, characterized by transition rate W. And if you define the population of the upper and the lower level and plus and minus, they, like very intuitively, one can derive this kind of master equation. And by defining the population difference, and this is proportional to magnetization, and you can basically relate your relaxation time to the microscopic process. So you basically have that this is the relaxation rate 1/T1 is proportional to the transition rate between the nuclear levels. If you now look at experimental measurements in this material, you see here, so the black squares, these are the T1 relaxation rate. You have a peak at the net temperature, which is the magnetic transition, in this case is around 7. And then you have this broader peak here, TP1, which this is in the paramagnetic phase. And basically, this is no magnetic effects is expected to produce this peak here. And so this has been conducted dynamically. And also, muon spin rotation measurements have been performed, and they didn't show any corresponding peak. And now with USR, you probe the local magnetic environment. So this made us think that this is related to some charge hopping process. And so what can be done is to fit this data with a model where basically we consider, so if we have something related to polarons, we have polaron optics. This displacement of charge is basically changing lattice distortions. Okay, so you have basically fluctuation of the electric field gradient around the nucleus. And this can be probed because the sodium atom, the sodium nuclei in our material have a spin larger than 1/2, so they have a quadrupolar moment, which couples to this electric field gradient distortions.
I can. Is there any? You only show the 1/T, T1. Yeah. What about the light shift around the 100? In the NMR, light shift even more.
I don't know about the night shift.
The shift is directly related to the magnetic susceptibility in the magnetic system.
Yeah, I don't know about that because some data are still under elaboration, these experiments. So far I only got this data. And also, I mean, this is similar to something that has been measured in, correctly, in some scope with the manganites, but they also connected this kind of peaks to polaron dynamics. So this was basically what we thought this can be related. But about night shift, I don't know the name. Yeah, so basically we can model this relaxation, this quadrupolar relaxation, and you basically assume that your perturbation have a correlation function which decreases exponentially with time and is characterized by correlation time tau with this exponential form, which is usually standard like in NMR experiments where you have some kind of lattice motion driving the relaxation, what you get is this formula, which is called BPP model, and this is also a standard from the 50s, which is usually used, where basically you have this omega 0, which is the Larmor frequency, and you have the acceleration time and the parameter delta squared, which is related to the height of the peak. And so basically using this model, you can extrapolate the activation temperature for the manifold process. And we can also, for Polarons, we can also model this within the FT. And this is usually done with a linear interpolation scheme, where you take two polaronic configuration, I and F, and you consider that the deformation, you interpolate the deformation between these two configurations, and you do one DFT calculation at each configuration. And you obtain this kind of opening barrier, where the height of this barrier is what you use as an estimation of the activation energy for the opening process. And this gave a very nice comparison with experiments. This is a kind of delicate point, but maybe we can, if you're interested in this, we can discuss it later.
Is the Polaron structure remains the same all the way to the S?
No, so basically you have the Polaron structure, the initial point, Polaron structure, and final point, and this is symmetric. You have the same kind of, usually you have the same kind of distortion, but then you interpolate the two structures. So at the middle point, you have something in between the two configurations. So the distortion are a bit smaller here, a bit larger here, and you have this kind of intermediate situation. So then we observe this peak also at higher concentration of calcium. And this is basically how the peak changes. And basically what we observe that the position of the peak, the activation temperature and the intrinsic correlation term of 0, it's basically the same at every concentration measure. The only thing that is changing is the height of this peak. So, and in here, when we rederive this model for the transition rate of the relaxation time, we basically obtain this formula for this parameter delta squared, which depends on the fluctuation of the Jahn-Teller distortion of the osmium oxygen octahedron. And in particular, if you consider only nearest neighbor opening, and also the fact that in all our calculation, all other modes were negligible, we get this expression where you have only the breathing mode, which is kind of unnatural because putting one more charge, your octahedron has to expand to accommodate this charge. And you have this also this tetragonal distortion related, as we will see, to the Jahn-Teller distortion. And when we look at the comparison between this formula, which is the red one, and the value obtained from the feed, we observe a very nice qualitative agreement between the data. And you see from also the FT calculation, you obtain always an insulating solution. You have a gap which is decreasing a little bit in the middle, but it's always open. And also got this very nice agreement where basically here only what we have is that these fluctuations are evaluated from the FT calculation, as well as the average distance between osmium and oxygen. And we also have that basically the capital Q is the quadrupole moment of the sodium atom. This is taken from experiments, and QOX is equal to 2 and is the formal charge for oxygen ions in the derivation of this model.
You have on this plot bipolar out here, something new, I think, in your presentation. Could you comment?
Sorry, what?
Bipolar.
Bipolar.
It's a two neighboring polarons.
So bipolar is why bipolar? We should go back. Can I comment this on at the end? Okay, because now we should go back. It's more a detail in this case. Okay.
Oh, okay, sorry.
Okay. So now at this point, as I told you at the beginning, this was one of the first cases with polaron material with strong spin-orbital coupling. So we wanted also to try to understand what was the role of spin-orbital coupling in this polaron formation. So what we studied is how the polaron energy changes with the strength of spin-orbital coupling, as you see in the plot on the left. And you basically observe that so the polaron is less stable as you increase spin-orbital coupling. So this C lambda tells you the strength of the spin-orbital coupling. One corresponds to the ab-initio value of the spin-orbital coupling term. And you see that this becomes less stable as you increase spin-orbital coupling. At the same time, so basically what you observe that is the Q1 mode, the braiding mode does not depend on spin-orbital coupling. It's always the same. All other modes were 0, but this 3. And you see that Q2 and Q3 and QXY gives almost no contribution to the energy of your system if you get this distortion. They were also quite small. Whereas the Q3, the tetragonal distortion, gives you an appreciable contribution at low spin-orbital coupling, which is quenched as you increase spin-orbital coupling, as it was in the Jahn-Teller impurity model by Strasser as constant that I showed you at the beginning. At the same, correspondingly, you also have that the amplitude of the distortion is decreasing with spin-orbital coupling.
So can I ask a question?
Yeah.
The unit of energy in the y-axis is per unit cell or per per unit cell? Yes.
I also question. In the calculation, you assume it's initial size is
It's long.
is already cubic. In
The supercell I used was not cubic. Because we had to find a compromise for the computational cost because this calculation was pretty heavy with spin-orbital coupling. So it was a square root 1 supercell, but we observed that was enough for polarons. We also repeated on a larger supercell, but also the results were basically the same. But the cell was not.
Cl is the strength of the electron.
Yes. So C is so basically what we have done is the DFT calculation. You have the strength of the sock comes up initial.
Okay. So you
get a
manipulate it
parameter to scale it. It was this C lambda.
Also, I have a question too. Is there any physical reason why the Q3 has lowest energy in the absence of spin-orbital coupling? I mean, in the presence of spin-orbital coupling, the 3 is most comparable with each other, but only Q3 has the lowest energy. So it should be related to the structure of the orbitals. You have the T2G orbitals, which you basically, when you do a tetragonal distortion, you have this orbital that goes down and you gain energy. And it should be related to that.
This must be something that the Q3 tries to mix the orbitals that SOC does not want to mix or something like this. They are kind of orthogonal. So SOC wants also to mix orbitals, but not those that Q3 wants.
So basically, from this calculation, what we observed is that in this system, you cannot really single out the spin-orbital coupling when you try to explain the stability of this polaron, but this spin-orbital coupling and Jahn-Teller effect are really entangled. That's also why we called it a Jahn-Teller spin-orbital polaron. So this summary, I hope I managed to convey you this message that in this class of material with strong relations, strong spin-orbital coupling, you can really have competing interaction, which which opens like to really interesting physical phenomena. And I would like to thank all the people involved in this study, and especially my supervisor, Professor Cesare Bonchini, and Dario Ferramosca, Leonid Poroski from the Polytechnique in Paris, the experimental teams did the NMR and Western measurements, the groups of Giuseppe Falloti, Samuele Sanna, Vesna Mitrovic, and also Professor Patrick Burgot and his PhD student from Tan for preparing the sample. And obviously, thank you all of you for your kind attention.
Okay, so it's a question and answer time. So do you have any question?
The geometric calculation by Kurowski were done for which part of the results?
For the multiplet structure. Here. So basically, we took the structure obtained in DFT, polaronic structure in DFT, and learned to perform the MFT calculation to obtain the multiplet structure, the Gram-State wave function.
And also the difference between, so the energy difference between the states. So
Yeah. This is the MFT. Yes.
Yes.
The manganite case is Jahn-Teller is coupled each other. What about in this system? Do you think of the collective,
So
cooperative Jahn-Teller is not?
2 points regarding it. So in the pristine material, without the polaron, you have some form of cooperative Jahn-Teller, which is coupled to the canted ordering. Okay, because you have this orthorhombic distortion, which has, let's say, one direction on one plane, and another direction on the other plane, as the magnetic moments. And there, that distortion is coupled. But the diagonal distortion of the polaron is not coupled. This is an impurity. It's like a Jahn-Teller impurity. And this is also why the impurity model calculation that I showed you at the beginning also agree with the calculation we did. So when I showed you this, these two trends, if you remember, corresponds to this calculation made by Stratstov with exact diagonalization on an Jahn-Teller impurity. They have the same qualitative trend. It's exactly the same. Because this polaron basically constitutes an Jahn-Teller impurity in this lattice.
So you use the U value around 3 electron.
3.4.
So overall, these Polarons they stay the same for like lower value of U, like 1.5 or.
So I haven't tried that because basically we started with this value of the U, which is the CFPA value, which is also the value that gave the correct magnetic ground state for the pristine material. And obviously, one should expect that some properties changes with the U value, especially the open value. That really depends on U value, but also if you use, for example, other function, you have to expect that changes. But in this work, we didn't try. We just started with this value. We said, okay, this is reasonable because of CFPA, because of the study made on the pristine material, and we just use that value.
And you mentioned that this value is not that small with respect to other 5D orbitals. So is it simply an outcome of CFPA, or one can understand why it's slightly larger than typically reference? No, that's not your calculation. I understand perfectly. I wanted just to know whether there was some ideas why screening is less efficient.
We didn't really work on that. Also because this calculation were done previously.
So it's the perovskite. So actually, right next to osmium, it's not osmium, it's something other, not accurate. So I think it's more localized, yes, and I think so compared to our previous classmate, yes. So
Are there structural phase transitions in these compounds? At some
so basically you observe So the phase experimentally seems to be cubic at every temperature, but you see a local distortion. You have Jahn-Teller distortions at about 10 K. But it's also true that this class of compounds usually shows a very small tetragonal transition, but which is really difficult to measure. So experimentally said, there could be a very small tetragonal phase at low temperature, but we were not able.
What is small?
Like C
Temperature or the
no, the ratio CA.
the order parameters, so to say.
Yeah, it's really close to 1.
And at which temperature should that happen?
It should happen around 10 K. Because basically what you observe is that you have one first transition at 10 K where you have a reduced lattice symmetry, and then at 7 K you have the magnetic transition. This is has been shown from NMR measurements.
Magnetic transition at 7K or 7K?
7.
7? Because what kind of thing? Your previous
From
showed 7.
ferromagnetic to this canted antiferromagnetic.
Oh.
Is there any structural deformation by octahedron rotation or octahedron
There is.
tilting?
So tilting, it seems there is no footprint of tilting, but when you have this transition at 11K, you have orthorhombic distortions. So basically this one. You have this one, and then, like, our calculation shows that there is also a component with this symmetry and component with this symmetry. Because these are the independent modes, and you can have something that is resulting from the mixing of these kind of distortions. But the leading one seems to be the orthogonal one, the pristine.
Can this quadruple dynamic contribute to the dynamic structure factor spin?
You mean the
Can this quadruple dynamic contribute to the dynamic structure factor when you measure the muon scattering?
You mean the quadrupolar interaction?
The dynamic of this polaron, can it contribute to the
I would say it is possible, but the point is that we don't really know what is the magnetic state of the polaron, because so far we didn't manage to study it. Because you basically have that. So that with the pristine material, you have non-zero magnetic moments with this canted phase. So then if you go on the other side of the phase diagram, you don't have magnetic moments, they're at 0, and you have these octopoles. But the magnetic transition in between is not really clear. And also the state of the polaron is not yet clear. All this calculation was performed with a non-zero magnetic moment, keeping the magnetic structure of the pristine material. Because from some NMR measurement, it seems that the concentration at which I've done the calculation, so 12.5, we are close to the magnetic transition, basically. So, but we don't know yet, which is the magnetic transition. To understand whether this magnetic interaction contributes to the opening process, we should first understand also what is the magnetic state of the polaron. This is kind of the next step we plan to do.
And the question on the slide 41. So in this case, you can get Q like temperature dependent Q, right?
Q1
and Q2.
This one.
Yeah.
So this model was, this should be this delta Q1, delta Q2, Q3, basically an average amplitude of this fluctuation when you have the open point. So imagine you have polaron, non-polaron. So you have different Q1, the two sides, different Q3. So during the open process, you have the So this lattice oscillating, so you take this as a kind of amplitude of this oscillation. But so it's temperature dependent. But the point is that the levels of detail in which this model has been developed does not give account for this. So because basically to evaluate this, I just evaluated them from DFT calculation, which is basically zero temperature.
So how you derive initial impedance for this?
And this depends on the phonon spectrum, basically. You have the temperature depends on the phonon spectrum. This modes, like inside, contains the phonon spectrum inside, so you should do this kind of calculation. But I mean, I think it's really complicated. I don't really know if someone has done something like that so far.
So the phonon spectrum depends on temperature. Is it measured experimentally?
I mean, usually I would say if you have the temperature effect on phonon spectrum. So,
but is there some experimental study of this in these compounds?
in these compounds, not.
So where do you get this temperature dependence from?
You mean?
Of the phonon spectrum, you said the phonons, or this is some.
I mean, no. I mean, in general, I would say that one can expect there is some temperature depends on the phonon spectrum. I'm not saying that it's like this because
perovskite in general are very harmonic.
Yeah.
So harmonicity resists with them for this class of materials. It's something one has to expect.
Yeah, I mean, close to phase transitions in some cases. Some soft phonon behavior, some structure. That's why I was asking about the structure.
Yeah, this is another point that would be interesting to study in more details. But so far we don't have.
So basically, in the slide 44, you study the zero temperature. Yeah, 43.
Yeah. Yeah. Yes.
Question? I guess that someone asked the meaning of the bipolar.
Yeah.
Yes, actually, yeah.
This is kind of in the debate, but to some extent.
Yeah.
That's why I don't repeat the question because I felt that uncomfortable.
So, no, it's not uncomfortable. But so usually in a previous study on Polarons in DFT, like it has been studied as the case where you start from an empty D shell, you had one electron. So you have a formation of one bands, basically. So you have one electron added, one band. And you bipolar on the other end were cases where you had, for example, two charges either interacting or the same sign. Okay, two polaron interacting to each other, and you would observe two. In this case, it's a bit different because we started from a D1 structure. So when you had one electron, you go to a D2 pin of the sign. And you also obviously observe two bands as in a bipolaronic case. Okay? So it was in this kind of loose way that
When they form a bound state, if they're close to each other.
yeah, but I can understand that it's a bit loose, as we always say, definition.
Like a superconductor, have two electrons, they interact with lattice and they attract each other.
Yeah. But basically, yeah, the main comes from this basically observing band structure, which is really similar to that case. But with this caveat, the situation is a bit different from usual previous calculations.
For this thing, this D2 polar in your calculations, you say you kept the magnetization of the side zero?
No, it's not zero magnetization. Actually, it's it's larger for this polaron because you have one electron more.
So they tend to align.
Yeah, but this is in no way we don't know.
Okay, any question? And thanks, speaker again.